Course 3, Lesson 106 is really just a short review of what we already know about the way scaling works when you have three dimensions meaning volume. So because it's a shorter review, this I think gives you more time to focus on your written practice. Try to get all of those right. Focus on the ones maybe you don't know as much about and ask me or a friend to try to get those figured. Please, again, don't leave anything blank or with a question mark. Talk to me if you really are wondering about something. Email me, whatever it is, and I will try to work on it with you either in a video chat or over email. Since it's short, I'm just going to read as you follow along with me. We've considered the effects of scaling bigger or smaller on perimeter area, surface area, and volume. The shape of the figure doesn't affect the relationship. Mabel collects marbles. Her marble jar is full there on the left. It's small, cylindrical. So she needs more room. She finds a new jar. The jar happens to be twice the height and twice the diameter of this smaller first jar. So she figures if it's twice the height, that means she'll fill the new jar by half. Instead, she finds it's like an eighth full. Recall that the volume of a scaled object doesn't increase proportionally to change in edge length because it's by 3 dimensions. For example, we have a cube that's 3 times the length, width, and height of a smaller cube. We must stack 27 cubes to reach the volume of the bigger cube. Since the 3 dimensions, length, width, height, were multiplied by 3, then you multiply 3 cubed, you get 27. 3 times 3 times 3. We can make the following statement about any scaled object. When the dimensions of an object are multiplied by a factor, the volume of the object is multiplied, or divided if you're getting smaller, by the cube of the factor, or we call it the scale factor. So remember, for example, with this cube analogy, we can use that. The scale factor is just 3, because for scale factor, you use edge length, and this edge is going to be a third of the next one. So if we're going from here to here, we'd say that the scale factor is 3 because its edge length is 3 times bigger than this just one. But because, well, let's go to area now. Area is a new dimension. It's 2 dimensions, length and width. So to quickly go area from small to big, we would say area, you would take scale factor squared. That's going to be the difference between the bottom layer's area and the bottom layer of this's area. Okay? Volume, 3 dimensions, we said, so you're going to take 3, which was the scale factor, and 3 dimensions means cubit, right? That's why we say the label for volume is cubed. And now cube 3, and you'd get the space inside, the volume, right? So to find volume, take the original side length proportion and cube it. For example, if you have a brick that's 3 pounds, and you get 1.5 times bigger with a side length, and all of them lengthen that same factor, what's the ratio of the volume of the large to the big? If the large and small bricks are made of the same mix of materials, what's the weight of the large brick? Well, let's start with scale factor here. If the scale factor from here to here is, they said, 1.5, we don't need to actually know what this dimension is, what this length is, because they don't ask for a final amount. They ask for ratio. Okay? So we just need to know that the scale factor is 1.5. What have we learned about ratios of volumes? Okay, let's look back up here again. For ratio of volumes, take the scale factor to the third. So we're going to cube the scale factor to find the ratio of volumes, as it's called. That comes to 3 1/4. Is that what that is, I think? No, 3 2/3-ish. Anyway, 3 375 thousandths. That's the new volume proportion. Now weight, they said it's 3 pounds. To find the weight, of the new one, you just take the new scale factor, 3.375 right here, and you multiply that by the original weight. That's how you'll find those. So this answer is 10 125 thousandths. Short lesson. Why don't you try A, B, and D? A, B, D, please.